Our next speaker also cannot be contained or constrained by any single discipline. Hanno Rein is active in several different departments, the Department for Physical and Environmental Sciences at the University of Toronto. He also enjoys an appointment in the Department of Astronomy and Astrophysics, a person who's active in a host of planetary investigations. Indeed, his engagement with the universe is manifold. He investigates such things as Saturn's rings, hydrodynamics, codes of development, and high-performance computing. Today, he's going to take us on an Earth-like exoplanetary adventure. Hanno.
Thank you very much. It's a pleasure to talk to you. So everybody recognizes the building, which is just full tall outside the door. Can anyone guess what the line is in the sky? It's the International Space Station. And if you look very closely, you can't really see it on the projector very well, but there's actually a small line just parallel to the very bright line. And that's the space shuttle Atlantis on its last journey before it just undocked from the space station and then flew parallel from our perspective and then landed a day later. So let me start my talk by telling you about my collaborators, because this was really a study that started here at the Institute. There was Yuka Fuji, who's in Tokyo, and David Spiegel, who was a member at the Institute here. Yuka was visiting, and I was visiting too, since I had left just a few months before. And we started everything here, so this is a truly Institute for Advanced Study result that you're going to hear today. Now, to bridge the gap from the previous talk, let me start with a quote. This is from Epicurus, and he was a man of many things, and he was quite ahead of his time. For example, he said this, quote, that there are infinitely many worlds, both like our ones and unlike our ones. This was more than 2,000 years ago. So let me show you where we are now. You can download this application for free. It's one of my outreach projects that I started, and I worked on it also while I was here at the Institute. So it's basically a map of the universe. And this is our solar system. Okay. That's the Sun, Mercury, Venus. There's the Earth. This is the Earth. If you zoom in further, you'll find out where we are. And if you hold up your iPad, and if the connection holds, you can find out what stars you're looking at. Oops. Let me try it again. So we're flying into our location in the universe. See where you're on the Earth, and you can see that we're just on the edge of sunset, so it's probably sunset outside. And you can hold up, and the connection is a little wobbly, but you'll find that you can find stars and planets in the night sky. And not only stars in our own solar system, planets in our own solar system, but stars that host planets in our entire galaxy. So this is what you see in the background. You'll see the constellations that everybody recognizes, but there are also these red dots. And every single red dot is a planet that we have found in recent years. So we zoom out a little, you can see the three-dimensional structure of the stars in our nearby universe. And again, every red dot is a planet that we found. They're not uniformly distributed because we don't look in every direction. We only look in certain directions. So that's why you see a lot of planets in one of the directions. Now the green dots maybe the most interesting ones. These are planets that have the right temperature for liquid water to exist on their surface if they were terrestrial planets. So if there's an Earth-like planet around it and it's displayed as a green dot in this graph, then it's potentially habitable. And that's something I want to talk about a bit more today. So as we zoom out, you can see that we're just beginning to map out the galaxy. The galaxy has billions of stars. And we're just searching the really nearby stars for planets right now because we need bigger and bigger telescopes to look further. So just by looking at the nearest stars, we found thousands of those planets. So you can imagine what else is out there that we don't know of yet. And of course, we're not the only galaxy in the universe. So you can zoom out a little more. And now every single of those dots is actually a galaxy, again with billions of stars in it, which host billions of planets. So this is about the observable universe that we found. These are all the galaxies, and eventually you'll reach up to the end of the observable universe that some other people here at the Institute study. This is the CMB. So if you want to play with it, just go to the Apple App Store and search for my name or search for the word Exoplanet. You can download it for free. So for the rest of my talk, I want to talk about what I did here at the Institute with those two other collaborators. And it's about finding life on those planets, or why it's so hard to find life on those planets. So I'm going to talk about three things. First, about biosignatures. What is a biosignature? What are we actually looking for? Number two, I'm going to tell you how we do this. We're taking a spectrum. And then I'm going to tell you about one of the complications that can arise if we do that. So let's start with the biosignatures. This is not what we're looking for. So this is not science fiction. We're really looking for signs of life, and they don't necessarily have to be intelligent life. We're looking for the very basic ingredients of life as we know it. So a better example is this one here. It's a picture from Yellowstone, and it shows two very different kind of life forms. One are the ones that you see in the background, which you're all familiar with, trees, plants, life forms that we interact with every day. But then in the foreground, you also see very different kind of life forms. These are bacteria that live in the very hot, near almost boiling water of the hot springs in Yellowstone. And you can see the different colors. It depends on what temperature the water is. It has different colors. Different bacteria live in different temperature zones. So this is kind of a nice picture because it illustrates what we don't know. What we're looking for is life that looks like a green plant. Okay? But there are many other forms of life that don't look anything like we're used to normally. And it's going to be very hard to figure out what we're actually seeing. I couldn't do this talk without mentioning Carl Sagan. And in fact, a lot that I'm going to say is what he thought about many years ago. He wrote a very famous paper, and he used something that people hadn't thought about before. He used a spacecraft that was intended to study Jupiter and the outer planets, and he used it to look back on Earth and to look at Earth as a planet. Although we're sitting on Earth and we can do all the experiments we want to with the plants on the planet, but he took a spacecraft that's coming from far away to look back on our Earth. How would Earth look like if we observed it from elsewhere? And what could we learn about the life on Earth by observing it from apart? And there are three important markers that indicate that there's life on the planet Earth. And if we go outside of science fiction area and we're not going to try to find radio signals of prime numbers or any intelligent signal, but just the chemistry, then let me show you what these are. So first of all, there's just the color of things. As I showed you before, the forests are green. They're green for a reason, because it's the most efficient color to absorb the sunlight and to convert the energy from the sunlight to some useful chemical energy in the plants. So if it's green, that means there's a deficiency in the red spectrum of the colors. So by just looking at the color, we can say something about what's on the planet. And if you just look around on Earth, there are not a lot of green things other than life forms. Okay? There might be some crystal that looks greenish, but it's not, on average, what you see. So if you find a green asteroid floating around in space, you would wonder twice what's going on this thing. So the color is just something very, very basic. Just one comment on the picture. This is obviously from the IAS outside. Does anybody recognize the person? He is in the room, or was in the room earlier. It was Peter Goddard, our former director. So the color is one thing, but what we really want to know is what is the chemistry of the life forms? What do they do chemically? And on Earth, we have two species of chemical molecules that are very important for life. And we find them in the atmosphere. So that's a significant difference now. We're not looking anymore at the color of the surface of a planet, but we're looking at what happens in the atmosphere of a planet. For the Earth, oxygen and methane are the two chemicals that are very important. As you probably know, most of the oxygen in the Earth has been generated by plants doing photosynthesis. So just by observing how much oxygen we have, we can say something about life on Earth. And similarly with methane, a lot of the methane in the Earth's atmosphere is created by life forms, mostly nowadays in agriculture, like rice cultures in Asia. In the Western world, it's more cows and animals, farmed animals, that produce a lot of methane. So by just noticing that there can be one of those elements in the atmosphere is very helpful. But what's even more helpful is if we find them both at the same time. If you just take methane and oxygen, it will burn. You can ignite it and it will burn. So by measuring both of them at the same time, we can pull into the equation many more constraints. We not only know that both of these chemical species exist on the planet or in the atmosphere of the planet, but how fast they are generated and how fast they are destroyed. It could be that we're just lucky and have a planet which had a lot of oxygen in the very beginning when it formed, and it never went away. But if we see those two species at the same time, it can calculate how fast they would destroy each other. And if this is much shorter than the lifetime of the planet or the age of the planet, then we know that it has to be constantly regenerated. And there are only so many things that can regenerate gases in the atmosphere, and we can conclude that it has to be life. So for those two molecules, if we have a lot of those molecules in one planet's atmosphere, we know that there has to be some life on this planet. So how do we make these measurements? How do we find actual signatures of those molecules in planets that are very far away? Well, we take a spectrum. So let me explain to you what a spectrum is. It's very simple. We're just collecting the light and we're putting it into baskets according to their color. You all had the experience of looking at a prism where white light is separated into its different colors. And light is made out of small particles which are called photons. So we're now measuring individual photons. We're measuring the light, the color of individual photons, and then putting it into different bins. That's all we mean by a spectrum, dividing the light into its colors and then measuring it. This is a plot from the Sagan paper that I showed you from earlier. So this is now a spacecraft that's flying away from us, but it's looking back onto us as it's flying through the solar system. And you can see one of those spectra that it took. So it tells you how many photons we've discovered for a given color. And you get a certain shape out of this spectrum. And now you can see lines in the spectrum, lines that come from gases that are in the planet's atmosphere. So for the Earth, there's a lot of water and CO2, so it doesn't reflect any of the light over here. And then there are a lot of other molecules that have smaller signatures, like methane, for example, which has a feature here. So by just looking at the color of the light, we can find out what's on the planet. That's what a spectrum can do. Now the question is, how well can we do that? And that's why I called the title An Inconvenient Truth, because I'm going to show to you a bit later on that the amount of information we can possibly get out of this kind of measuring is very small. And it just depends on how many photons we can collect, how much light we can collect to make this measurement. The first row shows you what would be a low resolution spectrum, so we have very few photons for a given color. And the bottom one shows you a higher resolution spectrum where we have more photons. So our statistics are going to be better on the bottom row than on the top row. The amount of information on the bottom is much higher. We can learn more. So ultimately, what this means in physical words is we are photon noise limited. We can just get as much information out as photons we have. If we find 10 photons that's coming from the planet, we can measure 10 colors for each photon, not more. There's not more information available. So to illustrate this, I made an animation. It's showing you a spectrum, and as the simulation goes on, we're collecting more and more photons. So again, it's color and the number of photons plotted on this axis. And maybe there's someone in the room who will recognize what this is. Let me start it again. So now you saw the answer. But as this goes on, you will see that we need many, many photons to get any idea of what the underlying shape of this curve is. Right now, it just looks like pure noise. There's nothing behind it. Okay? Just random collection of photons with random colors. And as it goes on, the more and more photons we collect, the more information we will get out. You can see it takes a long time because we need many photons. In this one, there are billions of photons that we need to collect. It grows exponentially fast, so it's not going to take too long. But now you can already see that there's something that we can learn, right? We have some peak here, which is going to be the Empire State Building, and there are clearly some more depleted areas. But still, there is a lot of noise on top of the signal. It's not a smooth line. You can see that the spread of these things is fairly high. And that's the inherent noise of the system. That's what we would later call photon noise. And now you can probably guess already what it is, especially if you've seen it before. But if you've never seen a skyline before, this might not bring a skyline to your mind just yet. So you already need to have an idea of what you're looking for. If I tell you which, I'm going to show you a skyline, you tell me which city it is, you might be able to guess. But if I tell you, well, what the hell is this, you might not be able to tell me. Okay, and this is the final answer. So how do we actually take one of those spectra of a planet? Well, we just want to collect the light from a planet. That's the entire goal. It's very simple. Okay, you can take a picture of with your phone of any light source, and you're collecting the photons of this light source. And your camera has 3 different bins, so it can measure red light, green light, and blue light. So we want to measure more than 3. We want to measure maybe 1,000 or 10,000 different colors. But in principle, your camera can do everything you need to do. The problem is that your camera can detect a bright object and a dark object only if they're almost the same color, almost the same brightness. So if they're different by a factor of, let's say, 256 or so, one object is 256 times brighter than the other one, then you can take a picture and both of them will have some information on it. If they're very different in brightness, then you will either overexpose your picture or completely underexpose the other part. The problem with exoplanets is that if we want to take a picture of it of an Earth-like planet around a Sun-like star, then the contrast ratio is not 256, it's 10 to the 10, so a 1 with 10 zeros behind it. So you can see that it's a very difficult task. This can be done for very bright objects, big planets that are very far away from their stars, so the contrast ratio is not so hard, but even then, it's a very hard task to do. So directly imaging planets to collect their light is very hard. There's one easier solution, which is a transiting planet. So there you just wait for the planet to go in front of the star. It's going to block out a part of the star, and some of the light from the star is going through the atmosphere. So you're not looking at light that gets reflected off the planet, but you're looking at as the light goes through. So it acts as a filter. And both of these methods can be used to take a spectrum of planets. What I'm going to show you next is how we estimate how good this spectrum can be. And I'm going to show you a few equations. Now, bear with me, the equations are not too complicated. I'm showing them only to you because these are all the equations that we need. It's a very simple model. It's just a basic geometry in physics. There's nothing model dependent that one could argue with or could say, well, maybe technology improves or something like this. These are basic fundamental physical limits that we cannot play with. So for a transiting planet, all that matters is the size of the atmosphere as it goes in front of the star. And then we can measure the amount of light that goes through the atmosphere and hits our telescope very far away. Similarly, for a directly imaged planet, so if we can take a picture with this high contrast ratio of 10 to the 10, then we can calculate how much light we get in a telescope from this. And it's a purely geometrical effect. You have a star which is shining onto a planet, how much light gets reflected. You can do it with you can explain it to a child, and he's going to get it right approximately within a factor of a few. So there's nothing model dependent. And that's why the result is so frustrating. These are the equations that include all the factors that it depends on. But what's really important is these two numbers, 1683 and 12.2. This number tells you the spectral resolution that we can achieve. So it tells you how many of those bins we can fill for a given planet. And you can see that the numbers are not very large. They are 1,000. So we can measure about 1,000 different colors in the best case scenario for an Earth-like planet. And with 1,000 different colors, you cannot tell too much. That's the point. If we take a transiting planet, then it gets even worse. We can only measure about 10 different colors, and that's it. Okay. So it's a very frustrating result, because this depends on no physical parameters of the planet other than its size. And if we restrict ourselves to Earth-like planets, then that's fixed too. It depends on how big we can build a telescope, but there are also physical limits. So what we put in here are the most optimistic things we can think of for the next few decades. Nothing like this has even been planned or built yet, or it's going to launch soon. So you would need something like a 6.5 meter telescope, so about the size of this room, put it on a rocket, shoot it into space, and then you need to get all the other things right as well. You need to plug out the entire light from the star to a factor of 10 to the 10 to take your measurement of the planet. So all these things are very hard, and this is the most optimistic result, most optimistic numbers. These are the purely fundamental physical laws that determine this limit. And then there are these other things that make things even more complicated. Okay? So as I already told you, it's really hard to build this imaginary super telescope. We can't do it yet, and if we build one, there are going to be another factors that will reduce this precision of the spectrum that we can take, simply because the telescope will not be 100% accurate. It has some efficiency factor, and if we just lose 50% of the light going through the front mirror and there's some efficiency factor, then we're already down by a factor of 2, and we're not going to get any spectrum whatsoever. So there are a lot of just technical things. Those ones one could deal with. One can always think that technology will improve and people will be able to build better telescopes or make them bigger. But then there are all these other things, and these are all astrophysical problems that will eventually occur. There are other signals there that we can confuse with the signal that we actually want to measure. For example, the zodiacal light. I'm not sure if anybody has seen it, but it's really hard to see it in an urban area like New Jersey. But if you go to Yellowstone, for example, where it's pretty dark at night, you see this shimmer of light in the night. And it comes from dust particles in the solar system, and the dust particles reflect some part of the sunlight. So if we're taking a picture of a planet that's very far outside the solar system, but we have this fog of dust on our own solar system in front, it will completely dominate our spectrum that we take, so we have to filter that one out. In addition to that, there might be the same dust particles in the other planetary system that we actually want to observe. So we have no idea what this is. For the solar system, we can at least measure how much that is. For the exoplanet system, we have no idea. And then there are things like star spots, so variable sources on the surface of the star that just change with time and change the color of the star. So this will all complicate things. And then there's just an upper limit on the integration time. So you can say we're in the business of collecting photons. So we just wait longer and collect more photons. If you have a camera and you set the exposure time longer, you can see darker objects. But there's an upper limit here. For example, for the transiting planet will go around the star and it will transit the planet once per year, because it takes it 1 year to go around. And then it's going to transit for about 10 hours. And within those 10 hours, you can do your measurement. But then you need to wait another year to do the measurement again. And after maybe 100 years, you might get tired and don't want to do this anymore. So there's an upper limit, and we can't improve it upon it. This is just a physical fact. So that's a very frustrating conclusion so far, and I'm going to make it a little worse before I'm going to make it better again. So this is the research that we've done on here at the Institute, which is a new false positive. False positive means it looks like a signal, but it's actually something else. So it's a false positive signal. So we think we see life on a planet, but turns out it's actually created by something that has nothing to do with life. The basic idea is very simple. So we want to find an Earth-like planet which has methane and oxygen in its atmosphere. Because as I told you earlier, if we find them both at the same time, then we can be pretty sure that there has to be life that constantly regenerates those two molecules. But what happens if we actually see two different objects and we take a spectrum of the two objects at the same time? So in the case here, it would be a planet which has an oxygen atmosphere and methane on a moon that's orbiting the planet. If we look at this system from very far away, you cannot distinguish the two bodies. And you would just take the spectrum of both of them at the same time. So you would think that there's a planet that has both of those molecules in its atmosphere. And they would have to be constantly regenerated. But now it's one planet and one moon, and they can just stay there forever, and they would not react with each other. So there's no chemical reaction going on, and they're stable. So if we see methane and oxygen, now it means there could be life, or there could just be another moon. One of those moons in the solar system has a lot of methane in it. It's Titan. If you just put Titan and the Earth and take a spectrum of them both combined, it looks like one of those objects. And this is the result of our work. It's a spectrum again, so you see number of photons and the color on this axis. And you see the different models here. The different panels from the top to the bottom have a high spectral resolution, a medium spectral resolution, and a low spectral resolution. So the lowest spectral resolution is what we can possibly do in many years from now with a perfect telescope. We can't do it yet. But if you compare the bottom two curves, they look pretty much the same. You need a very high resolution spectrum. If you compare the top two curves, the black ones, where you can see a distinctive difference between the two different models. But we will not have 1 million spectral resolution. This one is 100 and 2,000. So these are roughly the numbers that came up in the equation before. And just to illustrate it once more, if I overplot the bottom two lines, on one graph you can see that they're almost identical. It's really hard to make the distinction between those two. So this was the bad part. And when we did this, we were pretty depressed about how bad things are. If you talk to other astronomers, they will not necessarily tell you how bad things are. They want to build their telescope, and I'm all for building telescope, but the honest answer is that it's going to be pretty hard to do something like taking a spectrum of an Earth-like planet within our lifetime. But there are many, many ways to go further. So how can we, first of all, break the degeneracy of this moon-planet system? How can we make sure we're not observing a planet and moon, we're observing one planet that has both of these molecules in the atmosphere? Well, first of all, we get very lucky if we find one of those planets very nearby. The closer the planet is, the better it is. One of the candidate planets is around Alpha Centauri, which is one of the most nearby stars to the Sun. So if this is a real planet, and chances are not too bad, then we would be lucky, and we can do a lot of measurements with this planet. So the more planets we find, especially the closer they are, the better. So maybe we're lucky. Then if we cannot break this degeneracy, maybe we find one of those molecules that is such a strong biosignature on its own that we don't need to have two. But even in the case with the planet and the moon, we still know that there is oxygen and there is methane. If we understand this better, and if we have better models to tell us what does the oxygen do on a planet's surface, then we may be able to just say something by purely measuring one of those molecules. We can also look at things like time variability. The moon's going to go around the planet, so there might be times where we're not seeing the spectrum from the moon because it's behind the planet. So there are ways like this around it. And then, most importantly, we can relax our assumption that we're looking for an Earth-Sun twin. This is a very human-centered approach. We're looking for another Earth that's exactly like our Earth that we're living on, around the same star, the same kind of star that we're having as our star. But we can go to very extreme environments. And as I showed you before in the picture of Yellowstone, they're so extreme environments that we, many years ago, wouldn't have even thought about being possible locations for life. So we really need to broaden our search for the life forms that we're looking for, and not only look for Earth-like planets around Sun-like stars. I'm going to show you a few examples, or two. They're both from the pictures from the Cassini mission. And this is Enceladus. This is a moon of Saturn. So it's not a planet, but it's a moon. And what you can see here is there are geysers coming out of the moon. And this is water that's coming out of the moon. So there's liquid water on a moon in our own solar system that gets spilled out in space. Yeah, this is an ideal case to look for life. We don't need to go to a planet that's very far away. We can do this in our own solar system. And this is where I think we should be going for if we really want to find life. And here's another example. It's also from the Cassini mission. This is the moon Titan. It's the moon that we used as part of our false positive scenario where we have the planet and the moon and they're contaminating each other's spectrum. But if you just look at the moon itself, this is a highly interesting object. There are lakes of methane on it. And you can see the sun being reflected on the shoreline of this lake, on the moon in our own solar system. Nobody knows what could possibly go on in terms of biological chemistry on such an object. So these are the objects we really want to go for. Now let me show you one more object. I'm going to go back to the app. There's going to be a pretty exciting event happening next week, November 12th. Does anyone know what's going to happen on November 12th? I'm going to show you. So it's humanity's first attempt to land on a comet. It's a European Space Agency in the Rosetta mission. So we're here in the center. That's the Earth and the Moon. And if I zoom out, you'll see this orbit here with the name which I will not pronounce correctly. The numerical number is 67P, which is easier to pronounce. This is a comet that's between the orbit of Mars and between the orbit of Jupiter. And you can see this trail, the purple line that's going towards the comet. This is a Rosetta spacecraft that's intercepting the comet. It's going to try to land on it. So if we go to it, you can see the purple lines, which are the orbits of the spacecraft. So they do very strange-looking orbital maneuvers to approach the comet. They're very careful not to go through the tail of the comet very early on in the mission. So I think it's closer then. You can see that they're establishing an orbit around it. And they're trying to get closer and closer. And then on November 12th, they're going to separate a small lander from the spacecraft that's going to fly onto the comet, attach to the comet, hopefully attach, because nobody has done it before. It's a bit of a issue just sticking to the comet because it's so small. So you need to be very slow and very soft landing. And then we're going to know what's on the surface of this thing. This is a picture or a model of pictures that have been taken from orbit now around this comet. But nobody has ever actually taken a picture of being on the comet itself. So it's unlikely that we're going to find life form on this comet. But there's so many interesting objects just within reach in our own solar system that we could go to and explore more. We don't need to go to an extrasolar planet. And I think this is actually where I'll stop. Thank you very much for your attention. I'll put on some conclusions and I'll be happy to take any questions. Thank you.